Morning, guys. Today I'm going to go over the free response problems for AP Physics C that deal with kinematics and a little bit more, but it starts with kinematics and it has the calculus involved. You should have this handout for the work. So the 100 kilogram box shown above is being pulled along the x-axis by a student. The box slides across a rough surface and its position x varies with time according to the equation x equals 0.5 t cubed plus 2t, where x is in meters and t is in seconds. Determine the speed of the box at time t equals 0. All right, so to get velocity, I'm going to take the derivative of x with respect to t. So this is going to be the derivative of 0.5 t cubed plus 2t. And I'm going to get 3 times 1/2, which is 1.5 t squared plus 2t. They're asking us what it is at 0. And so this would be 1.5 times 0 squared plus 2, so 2 meters per second. Determine the following as functions of time t, the kinetic energy of the box. Okay, so the kinetic energy is going to be 1/2 mv squared. We already have a function with respect to time. For the velocity, need a little bit of drink. So I'm going to have 1/2. My mass is given, so that's going to be 100. And then I'm going to have 1.5 t squared plus 2, and that's going to be squared. So this would be the function of kinetic energy. Net force. F net is going to be equal to ma. How can I get A? A is going to be the second derivative of the position function or the first derivative of the velocity function. And so I can take the derivative of V with respect to t, and again, I'm going to use our rule to say that that's going to be 3t. So I'm going to have 100 times 3t. So that would be 300t. And again, I'm combining, right? This is involving energy and force, and they're asking for power next, but it starts with kinematics, so I thought it was applicable. The power being delivered to the box. So the power being delivered to the box, power can be written as force times velocity. So I can have my force function multiplied by my velocity function. C, the net work done on the box between 0 seconds and 2 seconds. So our net work is going to be our final kinetic energy minus our initial kinetic energy. And so I'm going to have 1/2, 100, 1.5. They're saying at 2 seconds. Minus 1/2, 100. I'm running out of room here. Maybe rewrite this. Amateur mistake. So 1/2, 100, 1.5, 2 squared plus 2 minus the initial, which is at 0. So this is 1/2, 100, 1.5 times 0 squared plus 2. then this whole thing, since it's the velocity, is squared for both of these. So I'm going to plug this into my calculator. This one is going to be 2 squared, which is 4. 4 times 100 is 400 minus, or times a half is 200. So that one's easy. This one's a little bit trickier. So I have 2 times 2 is 4, times 1.5 is 6, plus 2 is 8. 8 squared is 64. 64 times 100 is going to be 6,400. Divided by 2 is going to be 3,200. So the net work done is 3,000 joules. Would the work done on the box be greater or less than the answer in part C? It would be greater. How do I know that? They tell us in the description that it's a rough surface. So there must be some work done against friction. And again, we would say that friction is a non-conservative force. Remember those forces that we can't easily get the energy back from. That's just the answers. All right, a crash test car of mass 1,000 kilograms, moving at a constant speed of 12 meters per second, collides completely inelastically with an object of mass big M at time t equals 0. The object was initially at rest. The speed v in meters per second of the car object system after the collision is given as a function of time in seconds by the expression v equals 8 divided by 1 plus 5t. Calculate the mass of the object. Okay, so momentum is conserved. And we're saying that our initial momentum is just the car. So that's just going to be M1, V1 naught. And then I'm going to have the masses added together times V. All right, so this is going to be 1,000 times 12. This is going to be 1,000. We don't know the mass. That's what we're looking for. And they wrote it as big M, so I am too. But I do know the speed afterwards because they're saying that it collides, and I want to know the speed right at t equals 0. So I'm going to put in 0 into my function. So this will give me the velocity of the two of them together. And it looks like it's going to be 8 meters per second. All right, so I am going to get M by itself. So I have 12,000, and then I'm going to have 8,000 plus 8M. So I'm going to subtract an 8,000, which is going to give me a 4,000 over here, and I'll have 4,000 equals 8M. And I'm going to divide by 8. And so M is going to be equal to 500. I think that's correct. All right, so assuming the initial position of x of 0, determine expression for the position of the cart object system after the collision as a function of time. It's possible you guys haven't seen this yet in calculus, but I'll show you how to deal with it now, and then Mrs. McCullough will explain it better, I'm sure, because that's way more her cup of tea. So I want to get x, the position. This is going to be the integral of the velocity function with respect to time. So this is my velocity function, which doesn't seem to be fun to deal with. So I'm going to make a u du substitution. So I'm going to let u equal 1 plus 5t. And that means that du is going to be equal to 5 dt. And so that means that dt is going to be equal to du over 5. All right, so when I plug this back in for here, I have that the integral. I'm saying that dt is du over 5. I'm going to put the 5 in front. And then I'm saying that 1 plus 5t is my u. So I'm going to put this in as u. And then I'm going to take the 8 in front as well, because I don't need to worry about that integer, I should say. All right, so this is another thing I'm not sure if you've seen or not, but again, you will before the test. We have that this is the integral of du over u is going to be the natural log of u plus a constant c. All right, so this is going to be what x is equal to. And I'm going to substitute back in for my u 1 plus 5t plus c. And we're saying that at t equals 0, x equals 0. That's a given for us. So I can see what my c is, or if I even have to have a c. So I'm going to put in the 0 here, and I have 8/5 natural log of 1 plus c is equal to 0. Well, the natural log of 1 is 0, so c is equal to 0. So our function is just our 8/5 natural log 1 plus 5t. I'll give you guys a second with that. And again, you could always go to my YouTube channel and find the video if you want a little more time to get this done. I think you guys have done UDU. I don't think you've done natural log yet, but you've seen it once, and then by the time, I'm not going to put on a test for you, but by the time you see it more times, it'll be something you're convening with. All right, so I'm going to make myself some room. All right, so in the next part, we're asking for the resistive force. And so in this one, we're going to take our velocity and to get the force, I need the mass times the acceleration. So to get the acceleration, I'm going to take the derivative of this with respect to time. And I'm going to use the quotient rule for this. The way that it was taught to me when I was a little boy is that if you have u over v, it's going to be v u prime minus u v prime over v squared. I know they have like a clever like Heidi high over Heidi whatever, but I don't remember what that is. But this is how I remembered it. And so in this case, 8 is our u and 1 plus 5t is our v. And so my first term is going to be v, which is 1 plus 5t. times the derivative of 8, which is 0, so that's nothing. And then I'm going to have u, which is 8, the derivative of v, which is 1 plus 5t, which is going to be 5, over 1 plus 5t squared. So this is going to be what my acceleration is. And I'm going to multiply this by the mass. So so this is going to be 1,500 times that square should be outside of the parentheses. So our resistive force, this ends up being minus 60,000 on the top. It's kind of a gray area with this. Very often, I'm uncomfortable with not having units in on everything, but I realize when you're doing functions like this that it becomes really cumbersome to have units in for everything. All right, give you guys a second with that, and then I'm going to erase it and do the last part, which is our impulse. All right, so I'm going to erase this, scroll back up, try that again. There we go. All right, so there's a couple ways that you can do the impulse. You can take the difference in the momenta, or you can take the resistive force times the time, and you should get the same answer both ways. So you could take mv minus mv naught. So v at 2, v is 8 plus 1 over 1 plus 5t. So this is going to be 8 over 1 plus 10. So our velocity is 8/11 meters per second. This is at 2 seconds. At 0 seconds, we already said it was 2 meters per second. And so our final would be 1,500 kilograms times 8/11 meters per second minus 1,500 times 2. All right, we're going to go on to the next one, which has simple harmonic motion in it. A block of mass 0.3 kilograms is placed on a frictionless table and is attached to one end of a horizontal spring of spring constant K as shown above. The other end of the spring is attached to a fixed wall. The block is set in oscillatory motion by stretching the spring and releasing the block from rest at time t equals 0. A motion detector is used to record the position of the block as it oscillates. The resulting graph of velocity versus time is shown below. The positive direction of all quantities is to the right. Determine the equation Vt, including numerical values for all constants. All right, so this is going to be equal to, I know normally I would start with the cosine, but I'd have to have a phase shift in there, and this looks like negative sine to me, so I'm going to start there. So what's A? A is our amplitude. And it looks like our amplitude is 0.16. All right, how do I get my angular frequency? Remember, this isn't angular velocity, it's angular frequency. That's a different thing. So this is going to be equal to 2 pi over capital T. Well, what is capital T? Capital T is the time for one cycle. It's our period. And so this is going to be 0.7 seconds. So I'm going to have 2 pi divided by 0.7. And that I cannot do without a calculator. Almost 9. So why don't I just make it 9? Make our lives a little bit easier. All right, given that the equilibrium position is at x equals 0, determine the equation x of t, including numerical values for all constants. So this is how we can find out whether we have a c or not, right? So I'm going to get my position, and this is going to be the integral of velocity with respect to time. So this is going to be the integral Okay, so I know that I want to end up with this if I took the derivative of something. And I know that the derivative of, so I know that the derivative of cosine is going to give me negative sine. So I know that I'm going to have a cosine of 9t. And then I know that when I take this derivative of what my position is, I want to end up with the velocity function. And so I know that I need to figure out what I have in front of it, so when this 9 comes out, when I take the derivative, it ends up being 0.16, if that makes sense. So I want it to end up being 0.16. I know that it's going to be 9, and it's going to be 9 times something. And so this x that I should put in front of it should be 0.16 divided by 9. So it's about 0.018. All right, so x is going to be equal to 0.018 cosine of 9t plus c. And we know that x is at equilibrium at x equals 0. So that's our function. All right, calculate the value of k. So looking at our velocity, I can say that 1/2 mv squared would be 1/2 kx squared. And our x function will give us the amplitude for x. Our velocity graph will give us the maximum velocity. A 1/2 cancels out, lucky us. Our mass is 0.3. So I have 0.3 kilograms. I have a maximum velocity of 0.16 that we got from the graph. And we have a maximum displacement of 0.018, which we got from the integral. And then again, I'm going to need a calculator for this. And it looks like it's about 24. I got 23.7. What about 24? All right, on the dots below represent the block, draw and label the forces, not components that act on the block when the spring is compressed a distance d/2 and the block is moving in the direction indicated. All right, so it is compressed a distance d/2. It's not a rough. It's going to be friction because it's a rough surface the whole time. It's moving towards the equilibrium position. So this is the equilibrium position. So the block is going this way. There's going to be a spring force this way, a force of friction that way, a weight, and a normal. Now it is over here, but it's still moving this way. So that means that friction is still going to be in the opposite direction it's moving, but past the equilibrium position, the spring force would switch. And I'm going to have normal up and weight down. Draw a sketch of V versus T in this case. Assume there's negligible change in the period and the positive direction is still to the right. So our period was 0.7, right? So I need to get to 0, so that means at 0.35 I should have a 0.2. And I should have one in the middle here. All right, they gave us our velocity. Our velocity started at 0, and it went to 0.16. So this is going to be it should be getting smaller and smaller as our dissipating force friction cancels it out. I think that's it.